Our lecture today is going to pick up where the last one left off, where we were looking at electrochemical systems. And in the first part of this series of lectures, we basically did a thermodynamic background. And we talked a little bit about how to calculate the thermodynamic voltage for an electrochemical cell, whether it's spontaneous or galvanic, or if it is electrolytic or not spontaneous. And the place where we ended last time was on first calculating the theoretical voltage using potentials, right? Where the theoretical voltage is just the cathode potential minus the anode potential. And then the last thing we talked about was equilibrium. And, you know, in any system, equilibrium means that there's no change, right? For infinite time. And if that's the case in an electrochemical system, that means that there's no reaction because, I mean, obviously, if we have redox reactions that are happening at both the anode and the cathode, the electrons go through the external circuit. If there's no reaction, there's no current. If there's no current, there's no power. So equilibrium conditions for an electrochemical reactor really aren't particularly useful to us. And so we have to understand then how to enable electron transfer processes or reactions to happen. And of course, understanding this is the tenet of our class, right? It's about kinetics and about reactor design. And so I want to start off our conversation about kinetics, hopefully somewhere that you find comfortable, right? So we're going to talk about just chemical kinetics, and we'll do a very simple reaction, A goes to B. And then I will transition that discussion to then electrochemical kinetics. And hopefully that transition happens relatively smoothly. And if you guys have questions as we go along, just please come on in and feel free to ask, okay? So if we think about our typical first order chemical reaction where A goes to B, okay? We've actually talked about how all reactions we can think of as electron transfer reactions. And if you really think about what we said on the first lecture of this semester, that we are taking essentially the electron in the highest occupied molecular orbital or from the lowest unoccupied molecular orbital, and we're either removing an electron from the former or we're adding an electron to the latter. And this happens in all chemical reactions. And each of those electrons has some free energy that is associated with it. And I just show that here. And the x-axis, if you've seen a diagram like this before, a free energy diagram, is the reaction coordinate, which could be some physical thing. It could be a bond angle. It could be, it really just measures the progression along the reaction mechanism until you get from the reactant to the product. And the product is going to have some free energy either in the LUMO or the HOMO, depending on what it is that we're talking about. And the difference between the lowest point here in this, what's called a Marcus well, from the reactant and the product is actually delta G of reaction. And this is the thing that we would measure thermodynamically, right? Where we would measure delta G, or we would be able to estimate maybe even what delta G might be. And then we've talked about activation energies this semester, but we haven't necessarily talked about where they come from. And really the activation energy comes from the difference in the free energy of the bottom of this well to the intersection with the product. And right here, that's some state of the molecule that's called the transition state. And so the transition state energy minus the energy of this electron in the reactant is the forward activation energy. And the reverse reaction, where B would go to A, also has an activation energy that's associated with it. And that is the difference in its energy of the electron that's here all the way up to the transition state as well. And what that allows us to do is what we've done for a simple reaction A goes to B this entire semester. We can actually write rate laws that we should be very comfortable with, that we have when A is in equilibrium with B, the total reaction rate is just the rate of the forward reaction minus the rate of the reverse reaction. And of course, then if it's an elementary process, right, this is just the forward reaction rate constant times Ca minus the reverse reaction rate constant times Cb. And both the forward and reverse reaction rate constants have an Arrhenius type relationship, and they're related to these activation energies that we're showing here, right? And so we could, if we wanted to, derive some expression for the total that is just K forward or the forward pre-exponential factor times the exponent of minus EF over RT times Ca, and do the same thing for the reverse reaction. And hopefully, most of the things that we've talked about here, you guys feel comfortable with, that we've done this throughout the semester. Maybe the Marcus Wells is a new concept, but this is where we actually can even use like density functional theory, for example, to calculate what the activation energy might be theoretically. And that's something that is actually done all the time, and something that someone like Professor Hayden in our department does very regularly. He'll do DFT and then microkinetic modeling to actually model what the transition from the reactants to products looks like, and then to actually find what that transition state is and predict activation energies, which I think is really cool. Now, we talked about equilibrium a little while ago, and again, we said at equilibrium, this means that the total reaction rate is equal to 0. And that really just means that the forward reaction rate constant times Ca is equal to the reverse reaction rate constant times Cb. But this is actually given a name, and it's something we don't talk about a lot in our class, or in most kinetic classes, quite frankly. And this is defined as V0, or the exchange velocity. And the exchange velocity is actually a measurement of the kinetic rate, that the higher the exchange velocity, the better the kinetics, right? Faster the reaction proceeds. Now, we don't do this in chemical kinetics usually, but it is very, very common to do this in electrochemical kinetics. And it's the reason I defined it here. So that way you can have a little bit of a feeling for what that actually is, okay? So before I move on, any questions, anything that you guys are uncomfortable with that we've done so far? All right, good. So now let's talk about an electrochemical reaction and think about, why is this different, or how is this different than chemical kinetics? Okay, so the electrochemical equivalent of A goes to B is just O plus some electrons gives you R. And actually, one electron is the most common one. So O plus an electron gives you R. So that's our version of A goes to B. And we can write exactly the same type of expression, that the total reaction rate is equal to the reaction rate constant times the activation energy times the concentration at the surface. Remember, this is electrochemical reactions don't happen homogeneously. They're heterogeneous processes, just like the catalysis stuff that we've been doing in recent lectures. And because of that, the only concentration that matters is the concentration on the surface. So then that's minus the reverse reaction rate constant times its activation energy times the concentration of R on the electrode surface. That's what X equals to 0 is. And it turns out we can measure this directly using the current. And so we talked about, so current is coulombs per second. We defined N and F last time, right? N is the number of electrons in the reaction, F is Faraday's constant, and A here is the surface area. So this would basically give us moles per time centimeter squared, for example. And if you look at this, the way that we've defined our electrochemical reaction is that the reduction reaction is positive current, right? This is the forward reaction rate. So if we measure a positive current, that means that we have a net reduction at the electrode. And if we have a negative current, it is a net oxidation, okay? And I just want to keep this in mind because we're going to think about how electrons are moving and what this means. Now, we said in our electrochemical systems, we can't just change things like temperature and pressure because all we would do is change the equilibrium voltage. So we need to provide a driving force for these reactions to happen. And that is going to be the potential of each of those electrodes. And we're going to look at 3 different cases. And we're going to do this in the same context as the Marcus diagrams that we saw before, okay? And the first one we're going to look at is just that the potential is at whatever our standard equilibrium potential is, where the current is equal to 0. And what is happening? Then we'll move potentials and talk about what that means for the current, okay? And hopefully this will make sense. And the start of this is thinking about how potential and free energy are related to each other. So here's the case where the potential is the equilibrium potential. And you'll notice this looks exactly like the chemical case, and that's because it is. That when you haven't applied a potential to the cell or deviated from the equilibrium potential, nothing has changed. The free energy of the reactant and product are the same. But that measurement of the potential actually lets us know where this value is, or it lets us measure the free energy relative to our reference, which was the hydrogen evolution reaction. And most electrochemical reactions, right, are happening on solid electrode surfaces. And if you think about what's happening is that a metal, right, let's say our electrode is a metal, you're going to fill some number of orbitals, like literal orbitals, with electrons. And there's going to be some density of states that are filled. And that is called the Fermi level. Actually, E sub capital F is essentially the free energy of the filled electrons in our electrode. And we know what that value is because remember, delta G from our last lecture is minus NFE. And so what that actually means, if we look at this from the perspective of the reactant and the electrode, that we can only fill our density of states of our electrode to the free energy of the electrons of the reactant. And that gives us the potential. That gives us this, right? And we can actually define the highest occupied molecular orbital and look at the lowest unoccupied molecular orbital as well and start to think about what would happen. Okay, so this is sort of the basic understanding for how the electronic states in a metal and a reactant line up in an electrochemical reaction and how we actually measure the energy of that, right? The free energy that exists here, okay? Hopefully this isn't too new, but let's then think about what's going to happen when we move the potential away from this thing that we called the equilibrium potential, right? So we already said the Fermi level is this highest state occupy electrons in the metal. So let's then shift the electrode potential away from equilibrium. And first, let's shift it positive of the equilibrium potential. And remember, delta G is minus NFE. So when we increase the electrode potential, it has a negative effect on the free energy. So we actually shift the Fermi level down. So we've actually forced the density of states in the metal to shift to lower energies. And so what's going to happen here, right? We have electrons at a higher energy state than in the reactant than the metal. So what's going to happen? Well, we donate electrons from the reactant to the metal. And we usually call that an oxidation, right? The reactant gives up electrons to the metal. And from a reactant perspective, that's an oxidation. And so one of the interesting things here is that we're actually controlling the free energy of electrons in the metal with the potential, and that drives a reaction one way or another. What this also means is that when the electrode potential goes positive of the equilibrium potential, we have an oxidation. And I'm going to link this a little bit later on to what's actually happening in a real device, and even some of the things that you guys will do in senior lab with your fuel cell experiment. Now, this is more of an electron diagram type understanding of what's happening. We also could have made or come to the same conclusion using a kinetic argument, right? So we have this plot that I showed a minute ago, and we had the free energy of our delta G of reaction. We also had the activation energies. So now what would happen to this Marcus plot if we applied the same shift? And remember, we're controlling the metal. So we're looking at the free energy of the metal, and then what will happen as the reactant either donates or accepts electrons. So if delta G again is minus NFE, right, this negative matters. So when we shift to the potential positive, this well shifts down. And now we have new lines. And I know now there's a bunch of horizontal lines on this plot. So this first red line down here is just at the bottom of this energy well for this electron. And this top red line is the new transition state, right? It's where the product and the reactant are going to intersect each other. And just like we did before, we can actually draw a line from the bottom of this well up to the new transition state. And that's the new activation energy for the forward reaction. And we can do the same thing for the product, and this would be the new activation energy for the reverse reaction. So one of the things that happens in an electrochemical system is that the potential directly manipulates the activation energies for the reaction to happen. And in this case, when we move the potential positive, we've actually increased the activation energy for the forward reaction, and we've decreased the activation energy for the reverse reaction relative to equilibrium. And if at equilibrium, the rate is 0, what that actually means then is that if this activation energy goes up, this rate goes down, right? The overall reaction rate goes down, just like we would have expected from our class. And as this activation energy goes down, the rate here goes up. So if we started at 0, and then the rate goes down here and the rate goes up here, we're going to have a negative current, which, like I said a couple minutes ago, this means that an oxidation is going to happen, or at least a net oxidation is preferred. Okay. So we've established from two different pathways that when you want, or when an oxidation happens at an electrode or at the anode, that the potential has got to be higher than the equilibrium potential, or the tabulated standard potentials that we talked about last time. Okay. And hopefully you guys will, hopefully you can follow this okay, and that, this has made some kind of sense. And if not, let's just do it again. But now let's, and we'll go through the same series of questions for ourselves, but now we're going to look at what happens when the potential is is less than the equilibrium potential. So we're just going to shift it the other way. So we're going to start at this same diagram, right, where the free energy for our electrode and the free energy of these electrons that are in the reactant are at the same level, right, the Fermi level, at equilibrium. Now, when we shift the potential negative, or when we force the potential negative, remember, delta G is minus NFE. So that means that the free energy in the electrode is going to increase. So we're going to fill more We're going to fill more orbitals with electrons, or higher energy orbitals with electrons. Now the energy of those orbitals is higher than the reactant. So what happens? Electrons flow the other way, right? You want to minimize the free energy. So the way to do that here is to make this reaction happen, right? And that, when the reactant accepts electrons, we call that a reduction. And this, something very similar happens to the Marcus diagram here, where we started at the base case, but now, right, delta G is minus NFE. So as we shift the Fermi level here, we're going to shift up, right? So as the potential goes down, right, the energy, the free energy increased. And now we're going to have a new bottom of this well, and we're going to have a new intersection with the products and a new energy for the transition state, which means we can calculate these activation energies again. And one of the things that you'll notice here is that when the potential is below the equilibrium potential, that the forward reaction activation energy is lowered and the reverse is increased. And if we look at this again, that means that the rate of this reaction, if this goes down, goes up. And if this goes up, the rate here goes down. And relative to zero, that means that the current will be positive, or that we will have a net reduction in our electrode. And one of the things that we are able to do in an electrochemical cell is to then be very, very quantitative about how the activation energies are related to this shift in potential at each one of these electrodes, which is actually very, very helpful and very convenient. And so one of the things that we often will get then in an electrochemical cell is an equation that relates the current to potential, not necessarily to the activation energies as we've seen previously. And that's called the current overpotential equation, right? And so we said before that the current is really a measure of our reaction rate. And so that current is equal to this thing called I0, which is called the exchange current density. Or actually, I didn't write it as a current density, but this is called the exchange current. And this is essentially equivalent to the thing we called before the exchange velocity, which has that sort of sister term in chemical kinetics that we talked about a minute ago. So I0 is essentially a measure of the rate that O plus an electron goes between, sorry, I keep writing A and B. It's just a habit from class, goes to R. And so the rest of this equation has to have the forward reaction rate and the reverse reaction. And so this becomes I0 times the exponent of minus alpha F over RT times the potential minus the equilibrium potential times the concentration over the bulk concentration. And I didn't want to do a full derivation of this, minus the exponent of this thing, 1 minus alpha times F over RT times E minus E equilibrium times the concentration of R at the electrode surface over the bulk concentration of R. Okay, and here we have two sets of brackets. Okay, so this is basically the result of our expression for our electrochemical process. Okay, and it captures all of that behavior that we talked about a minute ago. But the thing that's mostly important, and the point that we want to make here, is not really about this equation and how to use it, right? For that, I mean, there's a lot of things you can do from here. You can even get valuable information about the reaction mechanism from this equation by measuring this thing, this parameter alpha. But we're not going to do that here. I think that's digging too far into the weeds. I just want to give you guys an overall understanding of what's going to happen. So what does this mean? Like, what does all of this actually mean in the context of a real device and what we've been talking about so far this morning? Well, it's related to the cell voltage. So remember, we said yesterday that, or in our last lecture, that the cell voltage was equal to the cathode potential minus the anode potential, okay? And if we want to look at this, well, this cathode potential, and maybe here, I'll do this first. Our cathode potential has two parts to it, right? The first thing is it's related to our standard potential, right? And then that potential is shifted by, whatever this equilibrium potential is. And maybe instead of calling it the standard potential, we'll just call it the equilibrium potential of the cathode. And I know that this equation might seem sort of stupid to write this way, but we have a name for this. We call this the overpotential. And it's just a measurement of the difference in the potential of the actual electrode from the cathode, or from the electrode. And we do the same thing for the anode as well. So the anode potential is then equal to the equilibrium potential of the anode minus the equilibrium potential. And this part is the overpotential of the anode. And here's what we write usually, then, that the cell voltage then equals the equilibrium potential of our cathode minus the cathode overpotential minus our anode equilibrium potential minus the overpotential of the anode. And the thing that we then get to is that the cell voltage then equals, if you remember, the cathode equilibrium potential minus the anode equilibrium potential is just our thermodynamic voltage. We did that in our last lecture. So this is just the thermodynamically calculated voltage minus the overpotential of the cathode. And a more common way to write this is actually minus the absolute value of these. And we won't get into why in this particular lecture, but it's a little more common to write it this way for a galvanic cell. So what does this actually mean? So to pull current or to force current to go through the electrode, we have to pay a penalty. And this is like the energy penalty to make the reaction go, And that means the faster the rate, the higher the overpotential. And we actually could have predicted that from this equation, that to make the reaction go faster, you have to get farther and farther from the equilibrium potential of each one of these electrodes. And one way to measure the efficiency of an electrochemical cell is actually just the cell voltage divided by the thermodynamic voltage. That's a very, very common way to do this. And if you take an example like we did last time, the proton exchange membrane fuel cell, PEM fuel cells usually operate at about 0.75 to 0.8 volts. And at their normal operating temperature of about 80 degrees C, we're at about 1.2 volts, right? And so we're in the 70% efficiency range. I mean, the exact number there is 67%, but we're right here in the 70% thermal efficiency range for these devices, right? So one of the things that we can learn about an electrochemical cell is that, for a galvanic cell, right, a spontaneous cell, that the thermodynamic voltage is always less. Oh, sorry about that. The cell voltage, little mistake there. The cell voltage is always less than the thermodynamic voltage. So again, right, thermo gives us the maximum possible work that could be achieved. And this is what we really get. And actually the difference in energy there, right? So all of the gases that are reacting in our cells have an enthalpy related to them, right? There's delta H. We're going to get some of that energy in terms of the electrochemical reaction, right? That's where this comes in, right? V cell. And the difference then between minus NFV and delta H of reaction becomes heat. And heat management is an important part of electrochemical systems design. And it's where the stuff that you'll do in heat transfer come into play, where you're going to use a combination of conduction and convection to control that. And it's actually where mechanical engineers spend a lot of time in fuel cell systems. They're very, very good at complicated fluid dynamics, much better than chemical engineers. So, we know that this is true. Now, for an electrolytic cell, remember, the interesting thing here is that for an electrolytic cell, the thermodynamic is negative, right? And we did that last time. That's how we know it's non-spontaneous. So that means that we're going to subtract again these overpotentials and get a value that's even more negative. Though we don't typically write voltages as negative values. So instead, the way that we look at this is that the absolute value of the cell voltage, which is the applied voltage, is always greater than the thermodynamic voltage. And that's all because of kinetics and how we're going to try to drive the reaction at the rate that we want. And it is possible to try to drive the rate so high that the voltage goes to zero. But again, that's not particularly helpful, right? And a lot of times devices like this, or like a fuel cell, we will collect something that's called a polarization curve, where you plot the voltage and the current next to each other, and you'll get something that looks like this, where you'll be able at the beginning of the experiment here to measure an open circuit voltage, which is very close to the thermodynamic voltage, but not typically exactly the thermodynamic voltage. And then this plot is kind of usually broken up into three regions. And if I, sort of draw maybe a few lines here, that in between these first two, the behavior here is dominated by kinetics. And this is a pseudo exponential, just like you would have expected from the equation that I showed before. This is actually driven by the movement of ions through the electrolyte, which we talked about in the last lecture. And over here, we're going to get to a point where we're limited by mass transfer. And we're going to talk a lot about mass transfer and its influence on catalytic reactions over the next several lectures. Starting, I guess it's the next actual lecture that we do. We're going to start talking a little bit about that. Okay. So, this is sort of the basic thoughts about how an electrochemical cell is going to behave, and why maybe on a battery, for example, you'll see that they only give a nominal operating voltage. It's because the actual operating voltage, like on an alkaline battery, the nominal is 1.5 volts. The actual operating voltage could be higher or lower than that by 0.1 or 0.2 volts, depending on the application. And that's because, some applications for, let's say, an alkaline battery is like the remote control for your television. And that's a very low current thing. So you're probably going to operate more like 1.6 volts or so, 1.7 volts. What if you had a flashlight that you, a high powered flashlight that you had to turn on? That's going to depress the cell voltage. Or even if you still have an electric shaver that actually runs on alkaline batteries, those are terrible in terms of rate. And so you're going to have to pay a huge penalty for that, not just kinetics, but also you end up paying penalties in terms of mass transfer as well. And if you're interested in how all of these resistances manifest I am teaching electrochemical engineering next fall, and we're going to do a bunch of case studies on devices that I've worked on. So we're going to talk about fuel cells, we're going to talk about electrolyzers, we're going to talk about lithium-ion batteries and alkaline batteries, and how to understand how all these different losses and how kinetics and mass transfer play a role in their behavior. I really just want to talk about one more thing. In the previous lecture, we said that these reactions all happen at the interface between the electrolyte and the electrode. And so the meaning behind that is that we must have three things present in order for a reaction to occur. Because remember, yes, we have electron transfer, so we need the electrode. We obviously need the reactant there. But remember, completing the circuit also requires the electrolyte, or for ions to move between the cathode and anode in that electrolyte. And so if we have to have all three of those things present, we call this the triple phase boundary. It's also referred to as the electrochemically active surface area. And this differs always between the actual surface area of the material, because you have to design electrodes not just to facilitate the electron transfer process, but also mass transfer, right? We need the reactant to get to and from the surface. And just a minute ago, I said that mass transfer can play a role in the behavior of these devices. So it might be possible to totally flood a cell with liquid electrolyte, for example. But what if your reactant is a gas, like hydrogen or oxygen or methane, that have very low solubility? Well, then the activity is going to be very low, and the kinetics are going to be very bad because the local concentration is bad. We also can think about this in terms of having things like solid polymers that might be able to conduct ions, but then we don't have the ability to move anything other than ions. Again, we're limiting the amount of reactant that can get to the surface. Now, we could put a lot of porosity in our electrodes, but then we might not be able to fill that with the electrolyte. And the contact between the electrolyte, especially if it's a solid, like in a fuel cell, for example, is very, very important to define where this triple phase boundary is. So a lot of electrochemical engineering is the act of trying to optimize all of these things inside of devices. And so we try, after we assemble cells or devices, to measure the triple phase boundary or the electrochemically active area. And there's two ways that we do that. And both of them are very similar to the chemisorption that I talked about of nitrogen a couple of lectures ago. And the two most common approaches here are measuring either the hydrogen adsorption on some noble metals like platinum that are able to do this, or to do CO stripping. And actually, CO chemisorption is a very common method in heterogeneous catalysis as well. Now, in heterogeneous catalysis, when they're doing this, then at the end, just like the nitrogen experiment, they measure like the volume of CO2 or CO that gets absorbed. In electrochemistry, we can do this even more accurately than you can for heterogeneous catalysis, because we can measure the exact number of electrons, because we measure the current. And so the two plots here are called cyclic voltammograms. And I know that some of you guys have never seen this before. Some of you guys have done the ferrocyanide experiment in junior lab, so you've at least taken some cyclic voltammograms before. But there are different regions that are active in these voltammograms, each corresponding to a different reaction that is happening. And what you do in this experiment is you start at your initial potential, and often you'll sweep the potential positive. And each one of these peaks is a redox reaction that's happening at that potential. And so each peak is a different reaction, right? And so as you go forward, there's multiple reactions that are happening here, here, and then when you go back, you cross the equilibrium potential for that reaction. And that means the reverse reaction happens. So the forward reaction, for example, here might be an oxidation, But then once you go negative, you would have a reduction. And then the same thing happens here. And this is a typical cyclic voltammogram for platinum. And there are a few characteristic regions in this plot that electrochemical engineers like to look at. The first one is this oxygen region, where actually the platinum surface starting from about here is oxidized. And that's where this current comes from. You're oxidizing the surface. And then atomic oxygen is diffusing, like through solid state diffusion, into the bulk, making platinum oxide. And then when we come back, that oxide is reduced. And so we get a peak for that. And then here, we call this the double layer region. And this behavior here might look very simple. But just like we talked about last time, supercapacitors have been a huge thing in electrochemistry and have really helped the design of high-powered systems. And this very simple series of two flat lines going forward and backward is why supercapacitors work. And I'll give another shout out to my electrochemical engineering class. We'll do almost a whole lecture just on that phenomena and supercapacitors. And then as you keep going negative here, you don't actually reduce hydrogen. Remember, we defined hydrogen as 0 volts versus as 0 volts. So in order to have hydrogen evolution, you have to go out to like 0 volts. And that's where this is going to go. You're going to have this exponential function down to here. But there's something in electrochemistry where you could have adsorption of a reactant at a potential higher than it's going to reduce. And that is a single electron transfer to adsorb a hydrogen atom. And so then on our surface, we can actually measure by taking the integral under this curve here, the number of hydrogen atoms that were adsorbed on our surface. And from different types of measurements in vacuum, we actually know how many hydrogen atoms can be adsorbed per centimeter squared on a metal like platinum or palladium or whatever. And so that's one way to get the surface area. We just take this data, we integrate under this curve, we get the electrochemically active surface area, and you can compare that to the real surface area that you took by BET, which we talked about before. Another thing you could do is to first take a voltammogram of platinum, let's say, with nitrogen around, right? So you still have these, just the hydrogen and oxygen peaks and the double layer here. Then you expose the system to carbon monoxide, which poisons the surface, but you then oxidize carbon monoxide by scanning the potential forward of its redox potential. And you'll get a huge peak when CO comes off the surface. And instead of the integral under this peak for hydrogen, it's the integral under this peak for CO. And that gives you, we know the number of electrons to go from CO to CO2, it is 2. And so you take the area under this curve, you normalize by NF, and suddenly you have the number of moles. In fact, it's the integral of I dt over NF. And that allows us in situ to measure the electrochemically active surface area. And like we said, for catalysis and for catalytic processes, the surface area is certainly the most important thing. And you're going to see that as a recurring theme as we start to step through the effects of mass transfer on catalytic processes, where you know that you created a catalyst that has some active area associated with it. How do we utilize that effectively? And that's a question, we're going to spend the last third of the semester on in our class. And it's something that there's a direct corollary to with electrochemical engineering as well. So hopefully in this, series of a couple of lectures, you can see how, electrochemical technologies can play a role in society, whether it's energy conversion or energy generation, energy storage. There's several industrial processes that are relying on electrochemical fundamentals and electrochemical engineering. And some of them are very good things, right? And some of them aren't so good, like corrosion. And corrosion mitigation, as I said in the last lecture, is a huge part of a huge employer of electrochemical engineers. Also electrodeposition and so on. So there's a huge number of possible jobs waiting out there for people interested in electrochemical engineering and electrochemistry. And the fundamentals are actually all rooted in our class, where we're talking a lot about how do you control reaction rates, how do you design reactors and control reacting conditions to either make a reaction that you want happen faster, or to minimize the rate of a reaction you don't want, right? And we've talked about all that stuff: rate, yield, selectivity, etc.